So, good morning. We go today through solutions of the work package number 2. There are 4 problems in this work package, and 2 of them are applications of lecture number 4 about circuit theory of transmission distribution in particular. Let's see, that's formulations. Right, 2 problems. And there are 2 problems about Coulomb blockade. Fine. So, transmission distribution from the current, I kind of expect you, if you'd better have the formulation of these problems with you. We start with a formula which is in framework of circuit theory of transmission distribution, expresses the current, which is a function of I, as let's see, do I need GQ here? It depends on normalization of the current. Let me be consistent with the formulation. Right, so it is in principle a sum over all transport channels. Each channel comes with its own transmission coefficient. Here we are. We are looking in the limit where channels are many, and we can replace this summation by integration. And the weight with which we integrate is a number of channels per unit interval of delta t is a transmission distribution. So we rewrite it as follows. Summation to integration, and the weight is here. Probability of transmission, the distribution of the channels, number of channels per interval of delta t. Okay, then the rest is following. And the question, and it is purely mathematical question, which I would like to discuss now, is how to revert this formula. So we know I of phi in terms of rho of t. We would like to get rho of t in terms of I of phi. If you just look at it, it looks like terribly complex problem. because what you have, in fact, integral equation for rho of t, and there are no ready methods to solve such equations, to revert such equations. Fortunately, the problem can be solved here, and okay, it has also some general significance, not only for quantum transport, but for modern mathematical methods. Okay, so the goal is to invert it. Right. The solution is explained step by step. Let me go through this. Let me repeat the steps and add a bit why these steps are done. Eventually, the idea is to look at zeros of this denominator. Right. And use the theory of complex functions. Right. Let me first pay attention to the fact that if you really regard phi as a real parameter, that will be smaller than 1, and we will never, denominator will never become 0. So we have to analytically continuate this equation. And there are many ways to do this. So what I write is just one of many ways to derive the same formula. Okay, the idea is that we introduce a variable z, which makes this denominator simpler. And this variable is 1 over sine phi over 2. So what is useful, we can see that if we divide both numerator and denominator by this sine squared of phi over 2, let me just do it. That all remains. Right. Interesting, what do we have here? That's again this trigonometrical exercise. That guy, let me rewrite it. It is useful formula which frequently gets forgotten, but I guess you know it from school days in some form of another. This is eventually sine phi. And what I wanted to know is to, I need to divide it by sine phi squared. All right. So that will disappear. Okay. Then I can introduce that and rewrite the current as a function of that. As far as the denominator is concerned, it is simple. It becomes z minus t. A little bit complex manner. We still have, let's see what we have. Cosine pi over 2 divided by sine over 2. We need to express it in terms of that. And it's been done for us. Was suggestive formulation. We can express it as follows. Imaginary units and GQs and work. Fine. Then if I sketch this function, only the part at given t as a function of z. So I have z plane. Then this function has a pole at z equals t, which is in the interval from 0 to 1. Fine. Each pole is in fact delta function. Do you see the formula? So right. I better take my glasses. Each pole is in fact delta function if you treat it correctly. To this end, we could consider z's, which are here slightly above, at positive imaginary parts, and z's which are slightly below. And normally, if we go to the limit, if we go with both points to 0, the values of the z's are the same, except the pole. Except the poles where it is a delta function. So we write it as follows. If it is a function of z, which is not a function of phi, I will write it. Write it later. I will look at the difference between z t plus small imaginary part minus I t small imaginary part. And that will become delta function by virtue of Cauchy rule. So we can integral over t. Let me put here some notes. Okay, so that denominator by virtue of Cauchy formula became like this, and we also keep rho and 1 is that. We also know that this is eventually a real part of this expression. There's imaginary unit here, there's imaginary unit here. Right, so real part of the current. How can I denote that the function of z? I put it here, z equals t plus I is eventually I just look at the formula which is given there. 2 pi gq t square root of 1 minus t. Real part. Okay. No, sorry. I meant to take delta function, so it is rho of t. Okay, we did it. If we are able to continue analytically this function to these values, we know what rho of t is. Fine. The only point now it's function of z. We need to recall that this is a function of t. And for this, we need to express, so we need to combine it. I wrote plus sign. We need to combine it with expression which relates phase and z. So this formula like this, which follows from this definition of yeah. Right. So with this we get the answer. So it it looks like a piece of magic, but it works only if we are able to make analytical continuation of this function to this region, right? So it is generally difficult to make it, for instance, by computers. There are programs for this, but they're difficult. It's a difficult mathematical task. But in simple examples, which we have considered during the lecture, it is doable, and eventually I will go for such an example. So we go to next problem, Ohm's law for transmission distribution. Let me make a photograph of the blackboard before I start with something else. Camera on. Fine. So what I want to do now, okay, here's the talk, is to find transmission distribution. Well, on paper, it's been formulated in a bit longer way, but in fact, what I want to find is a transmission distribution of a circuit, which consists of diffusive conductor and quantum point conductor ballistic contact. Right, so there is some conductance GD for diffusive one and conductance GB for ballistic one. And right, we need to denote the phases. So phi will be total phase drop across the system, and phase here in this node is going to be zeta. All right. So how do we proceed? What do we have to know? We have to know the current as a function of phi. We know the current phase characteristics of each element. For diffusive conductor, current is proportional to the drop of phase at this conductor. So current is G D times zeta. And the current here involves I-phi characteristics of ballistic conductor, which happens to be tangent of the drop divided by 2. Let us see the drop. This is the difference between phi and theta. So in principle, one can solve these equations. One has to solve these equations. For instance, one can express theta from this equation and put current here. It's going to be complex equation. One can try to solve it in a simple limit, and this is what we are going to do. So we look at these complex equations. Assuming something, we assume that the conductance of diffusive conductor is much bigger than the conductance of ballistic conductor. If we assume that, we are in an interesting general physical situation. We have resistive ballistic conductor like quantum point conductor, and next to this we have some scattering, some amount of impurities at which electrons can scatter. So in principle, first idea would be to forget about this, to consider it as a shortcut. But in this case, we know for sure that all transmission eigenvalues would be at 1. In fact, this is not true. We will see it now. There will be some distribution of transmission eigenvalues near 1. But what I how to proceed, how to simplify these questions, it is to know that first this drop is in general small. Right? Yeah, because this conductance is big, one compares to currents. This is big. This has to be small to compensate this current. Right, so now we did point 2. Now point 3 is the most how shall I say, constructive part. And we really need to do something. So let us see how we can solve it. First of all, we are told to go to phi, which is close to pi. First of all, let us understand why is it so, because now this current is in full glory. If set is small, it's a pi over 2, it diverges. Right, it is not really good to keep it at pi. One needs to have some small deviation. So let me call this deviation how shall I call it? Why don't I call it just delta? It's delta phi, but yeah, let me just save one letter with this. Good. So what we can do now, we can consider this limit and replace tangent with 1 over x, just to recall it's a function of tangent. And at pi over 2, it diverges. And it can be approximated with 1 over x. So let me put it here. The current becomes 2 GB 1 over x. 2 pi goes away, delta minus zeta. And that equals now it's an equation which we can solve. It's an equation which we can solve because in fact it's quadratic equation with respect to zeta. So let me rewrite it. I put this vector here. And what I will have here, let me collect this GD. So I have a quadratic equation to solve. Let us see, I guess I need to look up the solution. Right, so here we can now express zeta. And this is just current, let me write it down. It's current as a function of delta apart from the factor of GD that follows from this formula. Now one can imply general formula for reversion of transmission distribution in this case. Again, it goes through a couple of approximations, but it's algebra. I don't want to discuss it in detail. Right. Just let me spend some time to discuss the answer. Okay, that will be distribution of reflection coefficients. Reflection, it's 1 over t. So reflection coefficients appear to be small, and this is natural because we only slightly disturb the very resistive ballistic. So what are these? There is a coefficient. You don't have to look much at this. And significant part of the following. We have the ratio of two conductances, which, as you remember, is a large number. Let's see, a small number. Sorry. 1 over r, 1 is 1. Provided the expression on the square root is positive, which means that r is smaller than, one can derive it from positivity, that, let me call it some r naught, which is per definition is, let us see, 1 over r GB divided by GD. So the distribution, if I plot it, perhaps a bit not in a scale, is as follows. So the transmission coefficients going from 0 to 1. And the distribution, if I plot it, go like this. This is very narrow. Or not. Right. Now, what happens if you integrate the whole distribution? So one gets eventually the conductance of the most resistive part. Okay, good. Then the last task is to compute Fano factor, which is by definition is average. One is t. Same formula, but you just average T. One needs to apply it to this distribution. Again, one needs to make sure that transmission coefficients are small in comparison with one. So if there are no impurities, Fano factor would be just 0 for the whole thing, because as we know, the ballistic conductor doesn't produce any noise. So small diffuser conductor would eventually define this Fano factor, and that's is going to be, basically one needs to integrate this expression to obtain all right, so I guess I'm done with two problems which concern transmission distribution. Let me make a photograph of the blackboard. And I require a short coffee break for a couple. Let me resume recording. So now we turn to the problem of Coulomb blockade physics, and what we would like to look at is single electron transistor. To remind, it consists of two tunnel junctions. Tunnel junction is given by a symbol which is similar to capacitor, but two plates of this capacitor kind of drawn together to indicate that there is finite conductance, but also a capacitance. Okay, left junction, then the island, heart of single electron transistor, the place we store electrons in. Fine, another junction. And non-biasing. First of all, gate electrons. So here it's a real capacitor, no DC current would flow. Right, biased by VT. And here we have also voltage sources, right? And left, oops, forget about it. Fine. What do we need? Let's see. First of all, there is a kind of misprint in formulation. It's pretty suggestive misprint, but let me correct it. So electrostatic energy is given is proportional to the square root of charge, not to the first power, as it's written in the formulation. As nobody has noticed that so far, because you immediately see the square root here. Okay. In this energy, we only keep terms which depend on n, or number of charges in this island. And that's why I don't write any other terms. First task is to find the condition for Coulomb blockade diamond. What does it mean? We have 4 possible processes with which we can change the state of the transistor. We can add an electron from the left, from the right, or we can put it to the left, to the right. So one needs to figure out the energy differences associated with these changes. Let us see. Where can I find those? It's a bit clumsy expression. Perhaps I don't have to repeat it, just to recall how does it go. From the left. Electron comes from the left. This means that in the final state, electrostatic energy is n plus 1 electrons, while it was for n electrons before this transition. Also, we have taken an electron from the left, which means that its potential was right. So we need to subtract similar from the right. If electrons goes to the left, it the final state of the island is n-1. And we put an electron, so there's plus sign. Okay, that's how we make energy differences. Good. Next to it, in order to put everything together, we need to okay, we don't have a formula for Q here, but let me just do first of all, let us recall what is Q. Induced charge here in this formula is contributed by all capacitances and all gate voltages. So there is a real gate, but in addition to this, we also have contribution of the left voltage and right voltage. Here is Q. And yeah, first of all, we can do it in form of Q. And for instance, for this energy difference corresponding from the left, yeah, we just have to substitute N and subtract this 2. So let us see. That must be a correct expression. By the way, I have to stop a little bit earlier at 11:15, 11:20. We will see how does it go. Right, that's one of the conditions, and we can apply formula for Q. There are the condition still remains linear function of gate voltage and both voltages over here. Right. There are 3 other conditions. They are all done in this way, and the relation still remains linear. Good. So what will actually happen if we plot this 4 conditions? In the lecture, we have derived it for anti-symmetric biasing and for equal capacitances CL and CR. So the Coulomb blockade diamond as a function of Q was symmetric. So the reason for this is that in this case bias voltage does not contribute to Q. It depends on gate voltage only. So if it's otherwise, gate voltage, bias voltage, the Coulomb blockade diamond won't be symmetric anymore. Anyway, there will be some period, and there will be, let me just take another choke. So this is more common situation. So the diamond is slanted, it's not symmetric anymore. Anyway, we still can make periodic system of these diamonds, which will correspond to different states: 0, 1, 2, and so on. Right, so if you solve this problem, we have general linear relations which define these lines. And the qualitative effect that in general situations the diamonds got slanted. Right, what was the next question? Gives a region in VVG plane corresponding to 1-by-1 electron transfer. Or that is easy, that we have seen in the lectures. So it's kind of can be seen as inheritance of these diamonds. So let us continue new lines which define diamond with n equals 0 and n equals 1. So here possible charged states are either 0 or 1. So electrons go from the left to the right, I believe, and it goes in the following way. First, an electron comes here, and the second electron is blocked. Then electron gets out. Okay, let me perhaps sketch it with a timeline. This is time axis, this is n axis. So 0, 1. The process is like this. It remains 1 till the electron from the left will come. Then it stays in 1 till it goes to the right. Then again it is 0 and waits for transition from the left and then to the right. So the rates in these states are pretty much constant, but time intervals are random. So this is how transport occurs in this situation, in this particular Coulomb diamond. Right. Now we shall write master equations, and master equation comes rather frequently also during examination. So let us take time to understand Maxwell master equation for this. Let me make a photograph of the whiteboard again. Okay, perhaps I can keep the scheme. Let me remove this part first. Master question. How would I do this? It also belongs to master equation, perhaps it's helpful. What are possible states? They correspond to 0 and 1. Let me write a simple diagram representing the transitions between the states. So one can go from 0 to 1 with the rate we call FL, and it can get back. Okay, so let's sketch master regression. That can be done in real time. So what is the change of probability to be at 0? First of all, it can go to other state, to state 1. That happens with the rate FL minus sine P naught. And it could come to the state 0 from the state 1. Good. In stationary case, it is 0. I could write the same equation for P1, but this is not really needed. Why is it so? Because we would need 2 equations for 2 unknowns. For P0 and P1. But we know for sure that the sum of these 2 is 1. So I can use this equation to find, what shall I find? For instance, I can find P0. Let me rewrite it. 0 is GFL P0 plus GPR 1 is P0. Let us see how to solve it. I put this term to the left, this term to the right, changing sign. This remains gamma to the right, divided by the sum of 2 rates. Okay? So I find the probability to be in the state 0. Now I don't care much about probability, I care about current. And in this case, in stationary state, I would use the fact that the currents through both junctions must be the same. Okay, current conservation. So I need to look only at the left junction. So what happens in the left junction? Electrons tunnel with the rate gamma from left. And in order to do so, they have to be in the state with 0 extra electrons, right? So I have to multiply it with P naught. Electric charge must come somewhere. Okay, it's current divided by the number of electrons transferred per unit time. Okay, so now I substitute. Now I substitute, so I have G gamma F L gamma F right divided by the sum of the two. Now, goodness gracious, to the right. Here's the current. Fine, I guess we are. We have not yet done with kind of because the problem is to express it in terms of voltages. So now we need to go back to the energy differences, right? And use the general formula for the rate. The rate, whatever from left to the right, at 0 temperature is what? Well, corresponding, okay, let me write it for, since that we need from the left. Conductance of the left junction divided by E squared. And energy difference must be negative for rate to go. Right, so this is energy difference, so this is positive. Fine, so one just needs to substitute here, get the expressions for two rates, one can plot it, it's a kind of simple plotting exercise. Good, so I've done with single electron transistor. And there was an example of a more complex circuit. Let us see. I don't have that much time, but let me just start with the description of the circuit and we'll see how long we can go. So it's called double set because it has, in fact, not two sets in series, but the structure under consideration surely has two islands. So let me start with the islands, this most important part. So it depends on two charges. The state of the system is defined by two charges. And there is a chain of two junctions. So this is called 1, 2. This is called 2. And naturally enough, this is 1. Fine. What next? I'm gonna buy this circuit. That would be, let's see, V over 2. Minus V over 2, asymmetric bias, rather convenient. And okay, some gate voltages. Let's see, what was that about? Okay, there's some expression for charging energy. It's easy to write, it combines two capacitances. It is given there. So we know how to compute energy differences and compute the rates. So now we don't have much time. Right, we need to concentrate on certain transport direction. And let me assume, I guess that's what comes from the, as the calculation is done in a more general way. Let me assume that electrons just go like this. To make this to exclude many other processes which can happen in these junctions. How we solve this problem in general for master equation? That diagrams become useful again, and we concentrate on the situation where there are only two possible states. Do I write it correctly? So at any time, there's only one extra electron in this circuit. Or it can be two, sorry, it can be two. One here and one here. But there will be no two electrons in the same island. Good. I always start with diagram, right, in master equation. There are 4 possible states. Let me put it like this. Doesn't matter in which geometric order you put it, just make sure that you have all of them. Let's see, what do we do? What does this transfer provides in terms of transitions? So this G1, it will go when N1 is 0, irrespective on N2. So, and it will add 1 electron to the left. So there is a rate of this process. Let me call it G1, indicating which junction we have in mind. The rates in these 2 states can be different because electron here blocks. It might block this transfer a bit. Fine, G12, basically it goes from, you transfer electron from here to here. And let us see. G2, here it is, so an electron must be here. It starts from these 2 states and leads either here or here. Again, the rates here may be difficult because here the presence of the second electron is essentially changes energy differences. So let me indicate this fact is prime. So put prime here, is prime here. Now we are ready to write master equation, and I'm afraid I don't have time to go much longer with this. Let me just consider one node in this diagram. That one. Let us see. This is equation for 0, 0. And okay, we see the oncoming rates, which means with plus we have gamma, okay, gamma 2, and that comes with P10, 0. And outgoing rates, like this, gamma 1, and it comes with the same probability. So there is for this node, then we go through all 4 nodes, so through 3, because the sum of all probabilities is 1, so we need only 3 equations, not 4. Okay, with all these equations, we compute currents. Right, good. Thank you for your attention. Unfortunately, I have to stop here. I hope you have had fun. And I will keep the recording. I will post the recording of this session soon. Thank you for your attention.